Hello everyone. In this video, we are going to talk about what differentiation means. So, in order to understand differentiation, you need to have the basic idea. Um, just a second. Yeah, so you need to have the basic idea about slope as well as limits. So, if you have the basic idea of these two topics, then it's going to be really easy to learn differentiation. Alright, so let's start off. Consider a function y equals f of x. Just a second. Yeah. So consider a function y equals f of x. So it's a curve, and let me choose one point on the curve whose coordinates are x comma f of x. And let me choose another point on the same curve whose coordinates are x plus delta x comma f of x plus delta x. Well, what does delta x mean? Well, delta x is nothing but the change in x. So if I need to represent delta x, so this is going to be delta x, this length, that's just going to be delta x. So now if I ask you to find the average rate of change of y with respect to x, that is the average rate of change of f of x with respect to x, well, that's just going to be the slope of the secant line. So that's just going to be the slope of the secant line. Now what's this secant line? It's just a line that connects these 2 points. So the average rate of change of y with respect to x is just going to be the slope of this secant line. Let me call that ms. So ms is just going to be, if you use the standard formula for slope, you get, that is y2 minus y1 by x2 minus x1. y2 is my f of x plus delta x, and y1 is f of x. So I have f of x plus delta x minus f of x divided by x plus delta x minus x, y2 minus y1 by x2 minus x1. That's it. So this simplifies to f of x plus delta x minus f of x whole divided by delta x. So that's just the average rate of change of y with respect to x. Now what if I want to find the instantaneous rate of change of y with respect to x? Say I wanted to find the slope exactly at this point. Then what do I do? Well, what I'm going to do is, I'm going to bring this point, let me call that A and let me call this B. Now I'll bring this A closer to B along the curve. So this is my new point. It's the same point A. I've brought it closer to B. Now remember, this distance was delta x, so I've reduced delta x a little bit. Now how's the secant line going to be? It's going to be somewhat like this. Yeah, so that is going to be the secant line. Now let's say I brought this point A even more closer to B. So now how's the secant line going to be? Now it's going to be somewhat like this. Yeah, so that's going to be the new secant line. Now what if I told you that I brought this point A so close to B that you can't distinguish between A and B? I bring it so close. This is A and this is B. It's infinitesimally, the width, that is delta x, that has become infinitesimally small, meaning A is so close to B that, now let's see how the secant line is going to be made. So the secant line eventually turns into a tangent to this point A, to this point B. So it's kind of like a tangent to both B and A, but in reality it's not. But I've brought it so close to B. In that case, now what did I do? What process did I use to bring this A more and more closer to B? Well, I kept making delta x, that is this width, smaller and smaller and smaller. See, delta x over when point A was here and when point B was here, this was the width. When it was here, this became the width, and when the point A came here, this became the width. Now if I brought this over here, you can see, can you see that? Yeah, this is going to be, oh my god, I can't even draw it. So delta x has become so small that we can't even see it. So now here's where the concept of limits comes in. So here, if I take the limit as delta x tends to 0, of this thing, that is the average rate of change of f of x with respect to x, well, what's that going to give me? That is just going to give me the instantaneous rate of change of y with respect to x. So that's just going to be, now remember, f of x plus delta x minus f of x is nothing but delta y, right? It's this length, change in y, divided by change in x. And we have limit as delta x tends to 0. And this is nothing but, this limit is nothing but dy by dx. Now where did these d's come from? Well, it represents an infinitesimally small change in y upon an infinitesimally small change in x. So that is nothing but the instantaneous rate of change of y with respect to x. Now many of you still might have a confusion, so let's just take an example. Here I have a graph of y equals x square. So this coordinate is just 1, 1, and this coordinate is just going to be 2, 4. And as usual, you can find the average rate of change of y with respect to x by doing 4 minus 1 divided by 2 minus 1. But we are interested in the instantaneous rate of change of y with respect to x. That is the slope of the tangent to this point. How do we calculate that? Well, you can pick a point whose coordinates are really close to 1, 1. Like, let's say over here, 1.1, now what's going to be the y coordinate? 1.1 square, which is 1.21. So now what's the rate of change of y with respect to x going to be? Just going to be 1.21 minus 1 divided by 1.1 minus 1. So what's that going to be? 0.21 by 0.1, which is 2.1. So this is approximately dy by dx. Now what if we wanted an even more even better approximation? Well, let's just choose a point that is even more closer to 1 comma 1. Like, you can get infinitely close. So let's just take 1.001 or 1.0001. Now what's the y coordinate going to be? It's going to be 1.0001 into 1.0001. So it's going to be this. So it's going to be 1.00 2 0 0 0 2 3 zeros and 1 minus 1 y2. So this thing is going to be the y coordinate, 0 0 0 1. So this is the y coordinate. Now if I apply the formula of slope, y2 minus y1, and don't get confused, the coordinate the point isn't here, it's over here. It's so close to 1 comma 1. So 1.00020001 minus 1 divided by 1.0001 minus 1. This is equal to 2.0001. So we are approaching values closer and closer to 2. So if we get infinitely close to 1 comma 1, then we would have the perfect value of dy by dx, and that is equal to 2. I mean, you can make an approximation by looking at all of this. First we had 2.1, now we have 2.0001, and as we are getting closer and closer to 1 comma 1, our dy by dx is getting better and better. So, and the value is near 2. The values were near to 2. So the exact value of dy by dx is going to be just 2. Now, is there any other way that we can get to this result without having to go through all of this? Well, there is. We had just derived a formula, limit delta x tending to 0, f of x plus delta x minus f of x all over delta x. How do we apply that formula over here? Let's see. So this is equal to limit as delta x approaches 0, f of, now we know that f of x is equal to x square, so we have x plus delta x whole square minus x square, our original function, divided by delta x. Now if we just evaluate this limit, we'll have dy by dx. So what's this going to be? This is, if you apply a plus b whole square, x square plus 2x delta x plus delta x square minus x square divided by delta x, and delta x is still tending to 0, and this is equal to, so x square and minus x square would cancel out, so I have delta x Now I can factor out a delta x from here, so I'll have delta x times 2x plus delta x divided by delta x, and delta x is still tending to 0, and this is equal to, now I can cancel these delta x's, and I'll have limit delta x tending to 0, 2x plus delta x, which is just 2x plus, which is just 2x plus 0, because delta x is tending to 0, right? And this is nothing but 2x. Now dy by dx at x is equal to 1 was 2. So here also I'm getting the same result. 2 into x equals 1. And I have 2. So you can notice that you don't have to go through all of this pain. So you can directly use this formula, limit delta x tending to 0 for any function, not just x square, and you can derive, and this is a more general result, 2x. So dy by dx at for any value of x is just going to be 2x. So if I ask you dy by dx, this dy by dx is equal to 2 was at x equals 1. So if I ask you dy by dx at x is equal to say 5, what's it going to be? It's going to be 5 times 2, which is 10. dy by dx at x equals 20, 2 times 20, 40. dy by dx at x equals x, 2x. So here I have y equals sine x. Now our goal is to find the derivative of sine x. Derivative means dy by dx for sine x at x is equal to pi. Now I'll ask you one really simple question. What would be the slope that what would be the derivative of sine x at x is equal to pi by 2? Well, remember what derivative means. It's just the slope of the tangent, right? So the tangent would be somewhat like this, which is parallel to the x-axis. So what is the slope of a line that is parallel to the x-axis? 0. So slope equals 0. And slope basically means steepness. So it's not steep at all. The steepness is 0. So that's why I haven't chosen the derivative of sine x at x equals pi by 2, because it's obviously 0. Even over here it's 0. Even over here it's 0. Even over here. So these are called maximas and minimas. So we'll discuss about that later. So now let's find the derivative of sine x at x equals pi. Alright. Now what are the coordinates of this point? It's just pi comma 0. How did we get 0? Because the point lies on the x-axis, right? So it's 0. Or y equals sine pi, so sine x. So if x equals pi, y equals sine pi. What is sine pi? 0. So we have pi comma 0. Now let us consider another point really close to pi comma 0. Like how about pi plus 0.1 comma sine of pi plus 0.1. So that's the coordinates of this point. So pi plus 0.1 comma sine of pi plus 0.1. Now we can use the formula for slope, y2 minus y1 by x2 minus x1, and let's see what we get. We get sine of pi plus 0.1 minus 0 divided by pi plus 0.1 minus pi. So sine of pi plus 0.1, if you put that in a calculator, you're gonna get minus 0.09. So you'll get minus 0.09 divided by 0.1. Now what's this going to be? 0.0998. Alright. So now what's this going to be? It's going to be minus 0.998. Now this is really close to -1. So as you pick values, if you pick pi plus 0.000001, then the y coordinate is going to be sine of pi plus 0.000001, whatever. So if you pick points that are really close to pi comma 0, then this answer is going to become better and better, and you find that dy by dx at x equals pi is nothing but -1. So from here only you can say that it's really close to -1. So dy by dx is going to be -1 at x equals pi. Now so now you might be wondering, how do we use the formula, that is limit delta x tending to 0? Well, I've done that in one of my shorts, so I'll just leave a link to that in the description. So that's the basics about differentiation. So and there are many formulas like derivative of a power x, derivative of log x, natural log of x. There are many formulas. So but the purpose of this video was to give you the feel of derivatives or differentiation. So hope you enjoyed this video, and if you did, please leave a like and subscribe to my channel. See you. Bye.